All right, in this problem, we're going to be looking at the jackrabbit, the situation you were introduced to, and we're going to try to see how many different types of paths you may have sketched. So, as far as the shape of the jackrabbit, it looks pretty much like a parabola. You know, we have the highest point being the vertex, the parabola is pointing down, and we see that his height gets up to 3 feet. And the distance he jumps is 8 feet. So some of you may have drawn a path that looks like this. He starts here, he jumps to here, and he reaches his highest point halfway through that path. So maybe you did something that looks like this as your path of your jackrabbit. Now, somebody else maybe did starting at -8 and going to 0. That's 8 feet. And again, reaching its highest point. Maybe actually put that at 3, huh? Reaching its highest point halfway through the path. Okay, so maybe somebody else did this. And then finally, maybe one of you did this. You said, well, he jumps 8 feet, so let's jump equally on either sides of the origin, and then his height will actually end up being the y-intercept. So we have 3 different ways of looking at the path of that jackrabbit, and there may have been others. These are just 3. You could have drawn really an infinite number of different ways of representing the path of that jackrabbit. The point that's going to be important for us is the vertex. So our vertex here is at the point 4, 3. We have the point 80, and the point 00 as part of our graph. On the green graph, our vertex is at the point 03. And I'm not going to write all of the different ordered pairs on here. You could do that. But then in the purple graph, we have the point -4, 3. Again, 2 of them share 0, 0. And the others have some different x-intercepts. So moving on from there, if we wanted to try to write an equation, okay, so I could write for the red graph, y equals, now the problem is I don't know what my stretch factor is. So guys, I'm going to put in my holding, the letter that we use for stretch factor, which is a times x minus 4, because my vertex is at +4, plus 3. Okay, now for the purple graph, I could write an equation that says y equals a times x plus 4, because we're at the vertex -4, 3. And then finally, I could write y equals a times x minus 0 squared. Oops, I forgot squared on all of those, didn't I? Plus 3. So on all of these, I've got it in vertex form. The problem is I need to know what a is. Now, we know that this is the same path being represented on all 3 of these, so theoretically we should be able to get the same a value for all 3. Now here's what becomes important in our graph. We have an x and a y in all 3 of our equations. That x and y represent any ordered pair on my graph. So on the red graph, I could use 0, 0 as my x and y, or I could use 8, 0 as my x and y. Now, knowing that 0 is easy to work with, I'm going to go ahead and use 0, 0. So what I can do then is I can replace y with 0 and x with 0 in my equation. And what that does is it gives me a way to solve for a. So I get a times -4 squared plus 3, which is really 16a plus 3. Subtract 3, divide by 16, and I've got a. So now I have an equation that I can write for a, which is y equals -3 over 16 times x minus 4 squared plus 3. Now, if we did this right, it shouldn't matter which graph we pick, we should get the same equation. So let's try purple just to see how that turns out. So for purple, I also have the point 0, 0, or I have the point -8, 0. Now, just for fun, let's pick -8, 0, okay? So I would put 0 in for y, -8 in for x. And I'm putting this into the purple equation. And I get a times -4 squared plus 3. That looks really familiar. So I have the same exact equation, right, as I did over here. So I'm going to end up with the same stretch factor. So here I have y equals -3 over 16, x plus 4 plus 3. And then finally, let's go ahead and try the green graph. I have the point -4, 0. I also have the point 4, 0. It doesn't matter which one we pick. I'll go ahead and pick -4, 0 this time. And I'll put in 0 for y, -4 for x. And once again, we get an identical equation as we did in the prior two. So we get exactly the same stretch factor. So the reason I wanted to go through all of the different graphs you may have drawn is that I want you to see that no matter which one you drew, you should all get the same thing.